Um, Thank you, everyone. Today my topic is Eloq ConvergedDB on Apache Cassandra, which is built for the Agentic AI era. A brief introduction to myself. I'm Hubert Zhang Huan. I'm the CTO of EloqData. Prior to join EloqData, I'm the tech lead of Greenplum database and also the Apache Hawk PMC member. A quick introduction to my company. EloqData is building a modular database for the AI era. And we have a key innovation, data substrate. I will introduce it later. Here is the agenda of today's topic. First, I will give a quick overview of the new database paradigm for the AI era. And then we'll talk about how Cassandra's approach to AI. And later, I will introduce the data substrate. How does our data substrate power the Cassandra to supply more capability for the AI workload? And finally, I will introduce our latest progress, the Eloq ConvergedDB. Okay, so in this year's YC Summit, Andre Capacci introduced a new concept called the software 3.0 to building the software. So at the beginning, it's software 1.0, which is people write code to build their software. For example, Apache Cassandra is written in Java. It's a software 1.0. So later, we join the era of software 2.0, which is people tune the weight. For example, you can see in the graph, the Hugging Face. People just tune the weight, and then they can create their own software to create an image. Now we have entered the era of software 3.0. We don't need to write code. We don't need to tune the weight. We just speak in natural language, and the large language model will write everything for us. So it is called web programming. So the software 3.0 not only change the way we build software, but also drive the growth of database and data info. So here is a report by Neon. We all know Neon is acquired by Databricks this year for 1 billion. And Neon reported that the AI agent creates 4 times more databases than human. This is very surprise, right? Web programming is on the track to create millions of databases. I believe in the future, there must be millions of databases is created by the agent. So what's the agent created database looks like, and what's the new paradigm behind the software 3.0? So there are 4 features. The first one is multimodal. The software 3.0, the very single application need multi-data models, which include the document, for example, MongoDB, the SQL, the key value, the vector, and the graph. All the data models is needed, is required. What's more important is that we need the cross-model transaction. This cannot be handled by any existing database because they are only handle the transaction in their own data models. The second one is hybrid cloud. And we can see from the picture, the people say the natural language, and the web programming cloud SaaS platform will create an application for you. And then you need a database, no matter the Silverbase, Neon, or EloqData. So you don't need the vendor lock-in. You need the hybrid cloud and easy to migrate between the cloud. What's more important is it must be cloud native. For example, your database should use the object storage as your main storage. The third one is the faster scale. In future, agent-to-agent communication will increase a lot of traffic. And you cannot use just a single writer database. For example, the Silverbase and Neon, they are all single writer. you need a scalable data infrastructure. And the last one is experiment. We all know the large language model will make a mistake. So how to address this? Do experiment. The large language model can use a sandbox and try whether it's right or wrong. So sandbox is not just a compute resource. For example, in AWS, they have a firecracker. It's a very good way to have a compute sandbox, but in practice, you need your data, and the data is stored in the database. So it requires the database to have a branching, restore, and rollback features. For example, the branching, you must have a very quick branching. Just like we write code, we use a Git. So the database should have the same capability of Git to have the branching feature. Nowadays, we can think, for example, the PostgreSQL, MySQL. If we need to have an experiment branch, we need to copy all the data. It may take hours or even days. This is not acceptable. Okay, so how to choose the database in the agentic AI era? So we still need the traditional database. For example, the SQL and the MongoDB. They handle the structured and semi-structured data. For example, the travel gear, the user information, the billing information, and so on. So it's a kind of internet thinking, where data is a byproduct of the application. How to understand it? You can think for day one, you have no user, no order. So your database is very small. And when you have more user activity and orders, your data becomes large. So data is a byproduct of the application. It is very good at answer questions like what travel items did I print? Use Mongo or SQL, you can answer this question correctly. But in the agentic AI era, it is not enough because we have a lot of external knowledge, which is structured or even unstructured data. For example, we have the travel information, the travel guide, the tips, and the climate information, the weather, and the sensor data. For example, your blood oxygen, your body temperature, and so on. So it's a shift from the internet thinking to AI thinking. So in AI era, we need to think about how to effectively leveraging the external knowledge base, and data becomes the essential fuel. For example, in day one, your application has no user, but you need a lot of external data. You need to build the RAG, right? So here is another question. Are the items enough for a 3-day trip to a mountain with my dog? It cannot answer by traditional SQL database. It needs the database and large language model, and need the external knowledge. So it's a RAG. We need a RAG technique. So basically, the RAG is a retrieve and generate. Retrieve is to retrieve the semantic relevant document from your knowledge base. And generate is use a large language model to generate the final answer for you based on your retrieved results. Vector database is used in the RAG. For example, the document and queries are both mapped into the embedding and stored in the vector database, and it can enable a semantic similarity search. RAG is very popular, has many user cases. For example, the Q&A and the customer service chatbot, the legal document analysis agent, and so on. So Cassandra supply a vector search, which can do a RAG. This is Cassandra's approach to AI. So first, what's Apache Cassandra? So Cassandra is a highly scalable distributed NoSQL database. It is designed for a large amount of data. And for the AI workload, Cassandra is also to handle a large AI workload across many commodity servers. So Cassandra's the answer to AI is to supply a very scalable vector search. It has many good features. For example, scale out, concurrency, effective use of disk, and very efficient GC. And the last one is composability. So scale out is that many ANN vector search algorithms is just a single machine and in memory. And Cassandra's solution is to build the vector search with Cassandra's native distributed architecture. So it can use a storage attached index to integrate it with SS table. It can enable the transparent and scalable replication and search. The second one is GC issues. We all know the data will change, and the vector is the index, so your index should also be changed and be consistent. So how to handle it when your data is deleted or your asset table is compacted? So Cassandra's solution is use the storage attached index to make the life cycle of your vector index and your data together, and just use the SS table to handle everything. So in the picture below, we can see this is a compaction process of Cassandra to compact from the newer SS table to the older one. So your vector index and your data are both in the SST table. And the third is concurrency. This picture shows that when for example, the Python, it has very good performance for your vector search. But when you do read and write at the same time, since your write will rebuild the index, when the index is rebuilding, the performance of Python is decreased sharply. But Apache Cassandra's vector search remains very high performance. Effective use of disk, the Cassandra's JVector is also 4 times better than Lucene. The last one is composability. For the RAG application, we of course need not just the semantic search. We need some Boolean filter or some relation predicate. For example, I just want the color is red. So the solution of Cassandra is to make the query combining the vector similarity and the normal SQL predicates. And there is no need to have a separate vector database. Okay, and that's it enough for all the agentic AI requirements? The answer is no. From this example, I take my dog. We travel to New York. And then I flew back to Paris. So here is a question. Where is my dog Highland now? Using just the vector search is not enough. Because the vector search don't know the dog, Highland is my dog. Vector search can only search Highland is still at New York. So it requires a relationship. We need to store a relationship. So here we require a graph database to store this knowledge. Okay, this is how data substrate can powering the Cassandra to supply more capability for Cassandra for the AI workload. So what is data substrate? It's abstract all the common database features. For example, the distributed cache, the concurrency control, durability, scale, fault tolerance. We implement all these functionalities in the data substrate layer. Then we can assemble a database by choose a computer engine and a storage. For example, if I need a SQL document or graph, and storage, we can choose the object storage and also Cassandra. So from Cassandra's point of view, the data substrate can bring a distributed cache for it, and it can also have multiple API. It can support SQL document and graph. but the data is stored in Cassandra. So let's summarize the data substrate benefit for Cassandra. The first one is more elasticity. You can have a scalable buffer pool and a scalable redo logger, and you have more APIs. When you write the software with web programming, you don't need to care the API, and just the agent will write everything for you and ship it on the cloud. So EloqData is the first scalable and elastic on all resource type: CPU, memory, storage, and log. This enable you to scale just the right DB module for your workload's bottleneck, which can reduce your total cost of ownership. For example, you need more write traffic, you just scale the log. You don't need to scale the memory and the CPU, right? So let's illustrate the shift from a single server to a distributed architecture. Here in the middle one, there is the data substrate. We have a scalable cache and a scalable log. Scalable cache can help you have a unified management of multi-model data. And a scalable log, it has twofold benefits. The first is it supports parallel write, make you have more write capacity. It also supports parallel replay, and it can reduce your recovery time. So let's take a deep dive in how distributed buffer pool means. The first one, it is a scalable and a flexible buffer pool. Scalable means it can be sharded on different nodes. And the flexible means the distributed buffer pool can represent a table. For example, row 1 with a payload. Payload is also very flexible. It can be a list. For example, the CA is a state, and the 9.9 is a score, right? It's a list. The buffer pool can also represent a document. For example, the document ID is a key. The payload is a JSON. Except the scalable and flexible feature, it also supports the concurrency control. For example, the transaction T1 can read the row 2 in table and also write the document 1 in your document collection. So it's a cross-model transaction. This can only be done in the data substrate because it can both handle the table and also the document. We all know the memory is limited, so we still need to move the data in memory into the data store. Here is Apache Cassandra. We do it in a async and in a batch way, so it's more efficient. And also we have the failover case. For example, the memory node crash. Because we write the data to Cassandra in an async way, so we may lose some data. So here we have a distributed logger can do the recovery to make you keep 0 data loss. So privately we say the data substrate empower Cassandra with more elasticity. And here we show we can give Cassandra more APIs. From Redis compatible, we have a product called EloqKV. It is Redis compatible and also with transaction features. And also EloqSQL. It can give Cassandra the SQL API. EloqDoc is Mongo compatible. All the 3 databases, we can say that choose 3 out of 3. What does this mean? 3 out of 3. The 3 is there is a concept is called impossible trinity. Means you cannot achieve performance, scalability, and the transaction at all once. But the above 3 database with data substrate, you can choose 3 out of 3. Except the API will also have SaaS service called Eloq Cloud. We can have a scale to 0 feature. We can have a tiered storage, use the object storage and the local NVMe as your main storage. The free tier, we have a 10 gigabytes storage and 10,000 stable QPS. How we achieve it is based on the data substrate. Okay, finally, I will give a quick introduction to the Eloq ConvergedDB. It is a database that's built for AI era. Let's first take an example how we build an agentic AI application. This is a finance agentic AI. We have 4 agents: the compliance agent, the trade agent, the market analysis agent, and risk control agent. They communicate with each other and also the large language model. They need some data. The data we have the account balance data, the financial report data, the social media data. All the data need to be stored into databases. Here, traditionally, we need 6 or even 7 memory DB. We need 7 databases. Each database support is used to store different data models. For example, a financial report, they need to store into the MongoDB as a JSON format. They also need to do some trunk and calculate the embedding and store it into the Milverse or Python or vector database. And we also need to extract the relationship. For example, company A acquire company B and store this information into the graph database. So this architecture has many issues. The first one is that even for small application, we need multi-data models. And we can not ensure the consistent between data models or between database. And each database, we also need to consider the scalability and elasticity. For example, the PostgreSQL is a single writer one. It's not scalable. So one solution to this is use the event-driven model. The data is first right into the streaming, for example, the Apache Pulsar, and then flow to different databases. But this architecture also has some issues. For example, the data is eventually consistent, right? So our solution is to use a converged database powered by the data substrate. We use just one database, but supply multiple API. And it can do the cross-model transactions. So we can achieve the performance, scalable, and transaction all at once. And we can support the cross-model transactions. And we also can support the rapid scaling of the database. Okay, thank you very much.